I am Dr. Alex Bajcz, the quantitative ecologist for the Minnesota Aquatic Invasive Species Research Center, or MASERC for short, at the University of Minnesota. In this video, I'll be presenting principles and tips for designing great scientific graphs. This video is actually meant to be a complement to a website that I've built on the exact same topic, which you can access using the URL at the bottom of this slide, z.umn.edu/great_graphs, which will always be available at that URL. Here's why I think this topic is important enough to make a guide and a video on it. In science, your evidence for all your arguments that you're making are the data that you've collected. What we as scientists say, either in the discussion or the introduction, doesn't actually matter that much. We can say or argue anything we want so long as the editors and reviewers allow us to do it. What really matters and what can't inherently lie or distort or mislead are our data. Gathering and extracting knowledge from new data is the foundation of science. So, sharing new data with our scientific community is one of science's most fundamental rights, and the primary way we do that is via graphs. Said a little differently, graphs are how data are most often consumed in science. In fact, a large percentage of scientists focus primarily or even exclusively on a first pass on just the figures in a paper that they found, and they're trying to decide whether they want to keep reading it or not. So, in our papers, our posters, our presentations, our graphs are really the stars of our show. And the science of data visualization, how we should be designing graphs effectively for that purpose, is decades old now. We really understand quite a lot about how to make effective, great graphs. However, many of us have not been formally exposed to the results of that science, nor do we necessarily prioritize making great graphs when there's so much other scientific work to be doing. That's totally understandable. And of course, we can't all be experts in everything, right? Maybe just getting through our analyses was hard enough, let alone now focusing a ton of energy on visualization. As a result of all of these things, though, I think many of us produce graphs that leave something to be desired. That means the stars of our research shine less brightly than they could. I think this should and can change. I think we should start giving our graphs the same rigor we give other parts of our research. And that starts with understanding the core tenets of data visualization. Now, you might fairly ask at this point, yeah, but why bother, Alex? If others are getting away with ho-hum graphs, why can't I also? I can think of so many reasons that graph design is worth investing some time into learning, but here is just a brief list in case you need it. First, great graphs expand our reach as scientists. People consume, understand, and share great graphs with each other. They are really the most memeable aspects of science in that way. Great graphs are easy to pin up on a lab wall or pass around to colleagues because they deliver a lot in a small space and can do so captivatingly. Second, I know many scientists who are graphic masters. That's their calling card. It's a part of their brand. It gives me and others confidence in their work because it demonstrates a commitment to doing thorough, detail-oriented, and creative research. Third, graph making sparks creativity. It gets you thinking about your own work in new ways. It might even help you to enhance your own understanding of your work. Sometimes you can't even appreciate the most fascinating patterns in your own data until you've seen those data presented in a certain or unique way. Fifth, great graphs can fuel decisions when they can help our stakeholders make more informed decisions. Compelling graphs can also captivate and motivate receptive audiences to engage and to act, which a lot of us scientists want. Lastly, a great graph can just pack a real punch. It can convey a lot of complex ideas more succinctly than any other device could. So, suffice to say, I believe you have a lot to gain from leveling up your graph game, and that's why I wanted to create this graph design website and video series to help you be able to do that. So, I think the juice is worth the squeeze, so to speak. And I can promise you that there really won't be as much squeeze to learning how to design great graphs as you might initially think. I've got just 6 core principles that once you've mastered them will help you to make a great graph every single time. Before we begin, though, I do need to mention a few caveats with the content I'm going to be covering in this video. First, I'm going to be presenting a lot of what I'll call rules and quotation marks in this video. Rules, of course, made to be broken, as they say. No rule works in all situations. There's always going to be exceptions. However, I think it pays to understand what all the rules are because that will help you know when and how it would be appropriate to break them. I think someone much more famous than me said that once, so let's take their advice. Second, you may find that your discipline's norms or a journal's guidelines or something along those lines conflict with some of the rules that I'm going to be presenting here. Such is life, is all I can say to that. You may need to conform to the expectations of your audience sometimes, even when it means breaking a quote unquote rule. That does not mean that those expectations or conventions that you're going to have to be following are good. I want to be pointing that out, right? So perhaps you can start thinking of ways that you would half break them and thus move your discipline forward while still falling enough within the conventions not to ruffle too many feathers. Third, any graph is only as good as the data that are being put into it. Great graph design can unfortunately not rescue lousy data, nor lousy skill with your graphing software of choice for that matter. Knowing what you need to do to make a great graph is, of course, only half the battle, and I would acknowledge that right up front. You're still going to need to know how to do it. Those are topics for another guide, though, unfortunately, though I will have a resource to share about that at the end. Fourth, remember that there is no such thing as a perfect graph. While these rules are consensus-based and defensible that I'm going to be presenting here, the effectiveness of any particular implementation is always going to be up for debate. There's a lot of room for experimentation and subjectivity in data visualization. In part, that's what makes it fun to do. And it leads to my last point. Even at its best, graph design is trial and error and it's iterative. I know it is for me. Don't expect that you're going to be painting a masterpiece on the first try every time. This takes practice and it also takes receiving feedback from a trusted peer, which is something I'm going to talk about later on as well. So, with those caveats out of the way, let's go ahead and meet our 6 graph design core principles. First, choose the right graph for your data and your purpose. Second, respect your story and your responsibilities. Number 3, aim for universal design. Number 4, mind your channels. Number 5, stay professional. And number 6, remember that great graphs have great captions. In the rest of this video, I'm going to be going one by one through each of these core principles, explaining what they mean in practice and giving plenty of examples. I won't and can't cover each of these principles fully exhaustively. That is what the guide online is for, by the way. Instead, I'm going to be trying to give you a sense of what each of these principles is getting at and give you as many examples as I can to give you as many ideas as I can for you to have in mind the next time you sit down to design a graph. So without further ado, let's jump into principle number 1, which is choosing the right graph. And by that, I mean the right type or kind or family of graph. And that's really what's most important here. Yes, there really are right and wrong graphs to choose for each data set that you might be trying to graph. You can't just plug any old data into any old graph and get away with it. Without getting too technical here, one of the reasons for this is that we can distinguish 2 broad categories of data. There are continuous or numeric data like weights and lengths, and there's categorical or text-based data, things like species, sexes, and life stages. These are things you can't meaningfully put into numbers that aren't fully arbitrary. Because these types of data are very different from each other, so too are the graphs that were built to display them. Every graph type that you've ever seen was designed to show a specific flavor or mix of data and only that mix. So let's go ahead and look at some of the most common types of graphs to see what kinds of data they were built to display. First, we'll start with the age-old scatter plot. Here, points are representing individual observations, with each point's X and Y position indicating that point's values for two different numeric variables along the X and Y axes. If either variable along either of the axes here were categorical, a scatter plot would not work because we would not know at what position we needed to place the dots in that direction. In other words, these are essentially number lines, and if you don't have numbers, you can't place things along number lines. Now, you will notice that this scatter plot does hold a third variable that is categorical. It's marked by color hue. The color hue of the dots indicates something about what's going on with each of these observations. But that is a bonus. The first two variables in a scatter plot always have to be numeric for a scatter plot to work. Any ones on top of that are almost always going to be categorical. Now, if you have one numeric and one categorical variable, bar charts or box plots, as shown here on this slide, are your best choices. You can communicate the numerical data using these graphs along one axis, and you can use a single bar or a single box plot per category in a categorical variable in the other direction. While we're talking about bar plots and wrong kinds of graphs, I do want to pause here to mention that bar plots are only appropriate when you're showing counts or frequencies, how much or how large a fraction of something. Don't use bar charts to show, for example, means and standard errors of a group of data. As this visualization on the slide shows, the reason for this is that bar charts are really good at hiding what the underlying data look like in a potentially misleading or even dishonest way. In other words, many different data sets can generate the exact same bar chart. In each of these instances here, you should be using a box plot or a jittered dot plot to show these data instead, because these will show the shape of the underlying data set much better. Now, if you're thinking, gee, Alex, I see bar plots used to represent means and standard errors of fully continuous numeric data all of the time. And to that, I would say, yes, I bet you do. One estimate even suggested that 85% of scientific journal articles feature at least one bar graph, and many of these are inappropriate, just like the one here would be. So, all I can say is we've got a long way to go, but we have to start somewhere. So, if you've been using bar charts for these kinds of data in the past, it's time to start looking for alternatives because these are just not the appropriate graph type for these kinds of data. Now, if you have two categorical variables, what can you do with them? Well, you can show their joint frequencies or counts using what's called a contingency table, and I will show an example of that in a little bit. However, you can also show these data using what's called a mosaic plot, which is what's up on the slide right now. These are also sometimes called tree plots or tile plots. I don't think they look like trees at all, so I prefer mosaic plot or tile plot, but you will sometimes see them called a tree plot. Each tile in a tile plot has a width that is proportional to the frequencies along many categories in one direction, and a height that's proportional to frequencies in the other direction. So, the areas of the resulting squares give you a sense of the relative size of that specific subgrouping among the two categories. It does take a little bit of time to appreciate what graphs like these are showing, but I think they're quite cool and well underutilized. They're kind of like a stacked bar chart that's operating in two dimensions simultaneously, which is pretty cool. Maybe it goes without saying, but I would not use these unless the numbers of subgroups in both directions is relatively small. This is a 5 by 5 here, and that's probably about as much as you would want to push something like this. Otherwise, it can get very overwhelming to look at, or inevitably, some of the subgroupings are going to end up being so small that they're essentially going to disappear, which is sometimes unsatisfying. If you have just one continuous variable and you want to show how its values are distributed, a histogram or a density plot is going to be appropriate. What's shown here on the slide is a histogram. A density plot would be the exact same thing, except it would be a smoothed version. If you have just one categorical variable and you want to show frequencies or parts of a whole, you could do that with a stacked bar chart, which is what's here on the right-hand side, or with a pie chart, which is what's here in the center of this slide. However, I will warn you that data viz experts really don't like these two kinds of data visualizations for a lot of reasons. One of them is that they are very easy to distort. You can orient wedges in a pie chart in a way that makes them very difficult to compare or makes some wedges look a little bigger than others. They are also hard to read. It's very hard to compare the relative heights of bars that don't start and end in exactly the same places. It's hard to make comparisons on these graphs. It's very difficult if the wedges on a pie chart are in two different orientations to compare their sizes very effectively. And as these examples on the slide also show, it's easy to make these types of graphs completely overwhelming and on top of that, pretty ugly to look at. So these types of graphs are not graphs you can never use, but they are really only appropriate when you would need to divide up each pie or each bar into just a few pieces. If we're talking more than, say, four, you probably should be considering a different option at that point. If instead you have a lot of different levels in your categorical variable, one appropriate option for showing these data is actually a visualization known as a word cloud. Yes, these are a graph. What these do is they map word size to frequency of a given category. So categories that had more levels will show up as larger than other categories here. One challenge, of course, with these is the size of the text can get awfully small in some cases, and it can be much harder to read words that are oriented at an angle instead of flat. So that's another challenge with these graphs, but they can work quite well if you have a categorical variable with this many categories in it. Okay, that was a quick tour through some of the most common graph types that you're going to see out there. To sum this section up, what I would say is make sure you know what kinds of data you have, what kinds of data the graph you're trying to use is for before you use that graph type. No amount of graph design savvy is going to save you if you choose the wrong type of graph for the data you are trying to graph. If you want to learn more about how to choose the right kind of graph every single time, I actually have a guide to that very question that you can find at the URL on this screen, z.umn.edu/graph bestiary. A second point I want to make here is this. In general, I highly recommend using tried and true graph types for almost all graphs that you intend to be making. Don't reach for novel or highly unusual graph types most of the time, unless your audience is just as specialized, if not more specialized than you are. And even then, I think you should be doing it rarely. In fact, 95% of the time or more, one of the graphical workhorses should be carrying you. I've listed those here on the slide. Most of these should hopefully be familiar to you if you've been making graphs for some time. However, if any of the items on this are not familiar to you, I'd pause here and Google them. You might just not recognize the names, but I'm sure you have seen all of these graphs before, and that's kind of the point. We don't want to be making our reader have to learn an entirely new graph format just to be able to understand our data. It is useful to use a graph type that most of our readers are guaranteed to already understand. Relatedly, there's also right or wrong graph types and graphical elements for each given purpose that we may have for a graph. While graphs can be used just to transmit raw data to our readers, this is actually so inefficient that it should be very rare. We rarely have room in a typical paper, presentation, or poster for such a graph. More importantly, graphs are not a good representation of precision anyway. It's actually very difficult to accurately pull precise values from even a carefully designed graph. If precise values matter to your reader, it's better to just make the raw data available to them in the form of a table or a file via supplemental materials or via a data repository, which are easy to do now. Instead, most graphs should be providing evidence for an argument, such as that an experiment's results support or don't support the hypothesis. That means we're aligning the graph that we are building and its design with the purpose we hope that that graph will achieve in the final product. As an example, let's consider one of the most common elements of a scatter plot graph, which is a trend line or best fit line. A trend line is used to propose and highlight a relationship of some specific form, usually linear one, between two variables. In other words, it is showing either a hypothesis of a relationship or the result of some analysis that showed a potential relationship. If you are not proposing such a relationship or not trying to highlight one or argue that one exists, then it would be misleading and actually detrimental to include one on your graph. It would be at that point a distraction at best. It's also bad when you include a trend line, but didn't actually conduct any analysis to evaluate whether such a line was justified. It doesn't reflect the analyses you actually performed. And in a way, it's evidence for an argument that the rest of your product isn't making. So, generally speaking, your audience should be able to use your graphs to evaluate the analyses you actually performed and your evidence for the arguments that you're actually making. We should see our analyses in our graphs and really only those analyses. Another commonly misused element in graphs is connecting lines. These are lines that link two or more points or objects together within the plotting area, such as how the lines in a line graph link data points together into a chain. Connecting lines are intended to show something that's actually very specific, that the connected objects are linked, or in other words, dependent in a statistical sense. To get really technical, connecting lines show what's called pseudo-replication, essentially. Perhaps they're from the same study group through time, or they're from the same individual across multiple samples, or they represent the same property measured over a spatial gradient at a single location. So it's really only appropriate to be using connecting lines when such dependency exists within your data and you want to be calling attention to that dependency. So, for example, in this particular line graph, it makes sense that we are linking all of the pink points together because they are all measures of the exact same property over time. And so the next measurement was dependent upon the previous one's value. Another common issue is transformations, which are anything that means our raw data aren't raw anymore. We've taken the log, or we've averaged values together, or we've estimated a value, or what have you. The most common reason to transform data is to linearize a nonlinear relationship. The relationship that is shown in this graph is a log-log relationship, which means that we've log transformed both variables here, and only once we have done that does the resulting relationship look fundamentally linear. If you're not trying to imply that a nonlinear relationship actually normally exists between your variables, then it's inappropriate perhaps to transform your data to make it look like one might. You're creating a disconnect between your graphs and your analyses again in that particular case. Plus, transformations can be used to distort data to make them look cleaner than they really are. And readers must mentally undo any transformations that we do to interpret the data in most cases, which is cognitive work that is hard to do sometimes. So, transformations have to be used both sparingly and intentionally. Not every graph type is appropriate in every situation either. For example, scatter plots are not the best type of graph to use when you have so many points or so many points in the exact same place that you would get what's called overplotting, which is where so many points are sitting on top of each other that we can no longer tell how many points we actually have in a given spot. With substantial overplotting, we need to reach for other options. Some examples here would be two-dimensional density plots, or we could make the points in our scatter plot semi-transparent so that they somewhat stack on top of each other more clearly. Or we could maybe choose to plot just a random subset of the data instead. Similarly, distributional graphs, such as box plots, which are shown here on this graph, are not good when you lack a distribution in your data to show. Here we have several boxes, and I'll put that in quotation marks because they're really just lines here, either because we had too few observations in each group to actually show a full box here, or there's no variance in the data in that particular subgroup. Either way, we're collapsing down to just the median line that you are seeing in the center of all the other box plots. A rule of thumb for graphs like this is that you really should have 10 or more values in every single subgroup that you're going to be showing. Otherwise, a table of exact values would probably suffice. Or you could consider binning subgroups to make them larger so that they are actually as a distribution to show. Or you could just omit unvarying subgroups. Those are probably not terribly interesting for your audience to look at anyway. As one last example for this principle, I want to mention that sometimes no graph at all is the right choice for your product. Sometimes tables or text is the best and most efficient way to convey the data you're trying to convey. Ultimately, we want to be maximizing what's called our ink to information ratio. What's the most efficient way to be conveying our data accurately to the reader? What uses the least ink and space relative to the impact it ultimately has? And sometimes a table is the answer to that. For example, here's an example of a contingency table, which is something I mentioned earlier on. This shows the relationship between two categorical variables. Compared to a bar graph, which was what we otherwise might have used to represent these data, or a mosaic plot, or a pie chart, a single six-cell table is probably going to often be just as compelling, but it's a lot more efficient in terms of space. If we're trying to compare just two group means to each other, sure, we could use a bar graph, but text is often going to be way more succinct at conveying that result than a bar graph could ever be. So you needn't and shouldn't always reach for a graph. Sometimes text, a table, or making the raw data set available in some capacity would be better. Though I feel like I have plenty more I could say about principle number one, let's move on to principle number two, which is perhaps the meatiest one on the list. It says that we must respect both our story and our responsibilities as graph designers with our graphs. This principle acknowledges that every single graph we make is a trade-off. On the one hand, we want each graph we make to contribute to our argument that we're making. On the other hand, we must let our audience interpret our data freely and reach their own conclusions because that's at the essence of science. On the one hand, we also want to transparently convey our data then so our audience can do that. But on the other hand, we don't want to make our graph too complex or busy, or we will just confuse our readers. Now, it is challenging to design a graph that balances these competing aims, but I am here to tell you that it absolutely can be done. To do it, we may just need to learn to fight our first impulse, which is often to try to include every single thing we can in our graph. And then, if we maybe think we've overdone it, subtract from there. Instead, I recommend doing the opposite. Start by adding to the graph just one or two elements that are the most central to your message possible. Maybe that's a trend line, or maybe it's a key difference between two groups. Then add the elements that are needed to enable transparent and unbiased interpretation. Maybe it's an uncertainty band around your trend line, or maybe it's a confidence interval around a key difference. From there, we are only going to add additional elements to this graph if they somehow add to that transparency, to that interpretation, or to our message, and they don't exceed our audience's capacity for complexity. Speaking of which, if you don't know what your audience's capacity for complexity is, I'd say that's something you should try to find out before continuing rather than making a guess about. If you're planning on publishing in a specific journal, flip through some articles in that journal to get a sense of how complex the average article is in that journal. Maybe pick an article that's been cited many times as a classic example of what that journal might publish. This is also a good time to be mentioning that you should be cultivating a relationship with a graph beta tester, someone who's not involved in your research, who can look at your graphs and give you honest feedback. Your beta tester will often be able to tell you if your graph is too complex, but the hope is if you're following this framework, you're not making graphs that are too complex from the start because you're starting as simple as you can possibly get rather than as complex as you can possibly get. I want to explore that principle with a hypothetical with you for a second. I want you to imagine that you have two continuous variables and you want to argue that there is a trend between them that is useful and predictable. In that context, I want you to consider this graph that's now up on the screen. It shows a trend line and it shows an uncertainty band around that trend line. That trend line could be, the statistics would argue, anywhere within that gray band, and that's sort of plausible. I want you to consider this graph. What if I try to publish just this graph as it is right now? I think a lot of you would feel that this graph felt naked, like it's missing something. A lot of you would probably point to this graph and say, Alex, this is missing the raw data. Why did you not plot the raw data on here? If that is how you felt, I want to challenge you to stop and consider why you want the raw data on this graph so badly. After all, this graph shows our trend and it shows the uncertainty around that trend. Why should we add the raw data too? After all, doing so will add complexity. So I would argue that we need to be able to justify doing it. What specific benefit would we be gaining if we added the raw data points to this graph? Well, maybe you can argue it would add to transparent interpretation. Maybe we need readers to be able to see outliers in our data or something like that. Okay, that's a plausible reason, but I would counter argue in that case, why not just show the outliers then? What do we need all the other data points for on this graph? Okay, maybe you would counter and say, maybe seeing the distribution of the points is important. Okay, that's another reason that we might want to put the raw data points on this graph, but I would argue that the uncertainty band is already reflecting the underlying distribution of our points to some degree. The uncertainty band is wider where we have less data or more variable data, and less wide where we have more data or more consistent data. There are also other ways to show distributions without showing points. You could, for example, put a marginal histogram on this graph if you wanted to. Okay, you would say to that, well, maybe I think it's really important that my reader be able to read specific values off of this graph. Okay, we would need the points for that. But again, I would caution that reading exact values from a graph is tedious, and research has shown it's quite imprecise. So that's actually encouraging a bad impulse in some ways. We do not want to use graphs for precision. Graphs are about vibes, not about precision. So I'm not sure that that's necessarily a good argument most of the time. Lastly, I think we should be asking here, do we even have a manageable number of points to be showing? Will the level of overplotting be acceptable? If we put the volume of data that we have on this graph, will it actually make it harder to see the trend line that we want our audience to focus on? Would the volume of data be overwhelming in some way? Right? These are all important questions to be asking. So, I want to challenge you to stop and justify every single element that you want to add to the graph that you're making, right? There's an adage in design that a design isn't perfect when there's nothing left to add. It's perfect when there's nothing left to subtract, right? We want to start with the simplest graph we possibly can. And we shouldn't be adding things just because we think we ought to abstractly. If that feels like a radical idea, good. I think it is. And yet I really don't think it should be at the same time. Okay. I'd argue there's a common misconception that a lot of us hold about graphs, and that is that more is always better somehow. And really, the opposite is true when it comes to the design of something like a graph. Designers often talk about a concept known as cognitive load, which is the amount of mental work that is needed to take in everything on a graph, combine it in our heads, and conclude something about what that graph is trying to tell us. What many don't realize when they're packing their graphs to the gills in an effort to be more transparent is that by increasing the cognitive load of their graphs, by putting so many elements into them, they may actually be doing the opposite of what they set out to achieve. They may be making their graphs so obtuse and so overwhelming that readers can't or won't pull something out of them. For example, I recently encountered the graph that I'm putting up here on the slide right now. This graph is from the COVID pandemic, and it has a ton of really interesting information on it. But that's kind of the problem. It takes me, when I sit down to read this graph, a minute or more just to try to interpret part of it. I want you to pause the video here and see if you can do better than I can at interpreting this graph. Between all the transformations that were done on both axes, to the large number of countries that are shown on the graph here simultaneously, to the inclusion of text annotations on the graph, to the hidden third axis of time, which is in here along the lengths of every line, to the arrow tip that is seemingly used only once in the whole graph, to the inclusion of raw data points, which is what these white dots indicate. This graph exceeds my capacity to integrate its parts and pull any one single message. In this case, less would absolutely have been more, at least for me. So that's a misconception that we may have about graph design. Let's get all of our misconceptions about graph design out into the open so that we can start debunking them. First, there's this idea that graphs exist just to distribute raw data, right? Science is neutral. Science is just about delivering information. Thus, our graphs have to be very neutral too. This is noble, but it's misguided, as I've already said before. If all you feel that you must be doing is making your data available, simply sharing your data set on a data repository would be a more efficient way of achieving that goal than any single graph could be every single time. Contrary to popular belief, graphs are just not good for conveying exact values. Reading exact values from a graph is imprecise and it's difficult cognitive work and it's slow. Graphs should be about vibes, not specifics. That's a mantra I have come to hold. Second, there's this idea that you shouldn't use graphs to argue because science is impartial, right? We shouldn't be making arguments in science. We can't highlight key groups or color a trend line. That would be biasing our graph, right? Actually, I'd argue that that logic is totally backwards. What this misconception is really saying is we should design graphs that are making points, but we should be trying to hide those points in the graphs really hard so that our reader has to dig for them in the hopes of maybe finding them. When I put it that way, I hope the absurdity of this misconception jumps out. If you're trying to make a point, but you're purposely obscuring that point, that's actually a disrespect to your reader. They're supposed to be using your graph to evaluate your argument's credibility. If they can't even find the point you're trying to make in a graph, or they have to waste a lot of their time trying to find it, that's insulting. It's also insulting to assume that our reader cannot objectively evaluate our point just because we've emphasized it with our graph design. So there's this notion that one must give all elements equal weight in a graph, right? But this isn't true either. And this is related to that last misconception. You absolutely can make a point in a graph and emphasize some elements while downweighting visually the emphasis of others in order to do it, especially if this helps the reader separate primary from secondary information in your graph and thus find the point you're trying to make faster. And you can and should be more selective with graphs and elements in your graphs than you think you should be. For example, don't include 6 graphs when one will do. If some groups are poorly represented or they're uninteresting, cut them or bin them. If a pattern is inconclusive and that isn't the point you're trying to make, don't show that graph. Graphs you should view as being a premium item. They're a lot of work to make and they take up a lot of space. So we should be reserving them for the premium results of our work and not throwing them out casually. Now, of course, the asterisk here, great scientists don't hide inconclusive or contrary results. I am not saying that you should. What those scientists do, though, is make those kinds of results part of their message. And then they design their graphs to convey that message. And at the same time, great scientists don't dwell on things that aren't worth dwelling on. So you need to figure out whether your inconclusive or contrary results are a part of the message or a part from the message and tailor your graphs accordingly, including maybe not making graphs for those particular results. For the rest of this section of the video, I want to be giving some specific examples of this principle in action and touching on those misconceptions I just introduced. First, as I alluded to earlier, think how insulting it would be to argue in the text of your paper that a trend exists between two variables, or maybe that the trend is different for two subgroups, but then plot those data and not plot the trend in your graph that you are arguing exists. At that point, you are basically prohibiting your audience from evaluating your argument successfully, right? To be able to do that here, I'm now going to have to imagine the trend lines that might exist through these data. That's work that I, as a reader and evaluator, shouldn't have to be doing. It's wasting my time and energy, and it's weakening my ability to be able to actually evaluate successfully because I may not put the trend lines where they actually belong or where you're proposing that they ought to be. Secondly, let me maybe open your eyes to how powerful color and desaturation can be. I want you to look at the tile visualization that's shown on the slide here. Where are your eyes drawn in it? It's obvious, right? Where the researcher's message is in this graph. It's wherever the graph is pink. So it's easier to evaluate that message because no time is wasted in trying to find it. And at the same time, nothing has been hidden or lost or thrown out here, right? All the data are still here that are important to evaluate the argument being made. They're just in gray, which is a way of saying they're desaturated. I can still consider them however or whenever I wish, right? So this is a lesson that we can use desaturation to emphasize elements and by doing so decrease the cognitive load of the graph because the reader is now encouraged to ignore aspects that are not essential to interpret, at least at first. I have the choice now of whether or not I want to engage with the gray content on the slide, which means there's less I need to integrate right up front to pull a message from it. Next, here's a graph that forgets that less is more. Now, I want you to look at these 8 panels in this graph, and I want you to consider what types of patterns are visible in this graph. Here, I want you to do some rounding because you could argue that each of these 8 trends or patterns in these graphs are different, and that would be valid. But I'll tell you that to my eye, there are 8 subpanels here, but there are 2, maybe 3 broadly different patterns that I can discern. So we should ask as graph designers in this case, are all 8 panels here necessary? Could we have picked an exemplar of each pattern and omitted the rest? It's not like we have to throw them out. They could go into supplemental materials or be made available in a data repository, right? We have to respect that our readers have a capacity, and so too do our outlets. Journals only have so many space in them, right? We do not want to be wasting our readers' time or our journal's space on graphs that don't advance our argument in new directions. Arguably, there's really only three directions we need to go in with this graph, and yet we've got 8 panels in it. That's kind of a waste. Here's the same phenomenon, but on a smaller scale. In this bar graph, we have 17 different subgroups on the x-axis. That's a lot. And yet, most of them are actually quite poorly represented. You can't even see where the bars come up to here. They're invisibly short. Do we need all these subgroups to convey our message? What would have been lost if we had omitted the 7 lowest groups here? Or maybe we bin together several of the groups into an other bin. Could we have maybe just gone with 3 or 4 exemplars here too? Something at the top of the range, something in the middle, something a little lower, and something really lower still. It depends on the message the graph designer is trying to convey with this graph, but we may have been able to convey a similarly effective message here with quite a lot less data shown, which would have made it easier for our audience to pull that message out of the graph. As one last example, I want us to consider error bars for a second. Recall that error bars are meant to show that we should be comparing two groups to each other, right? To see whether those error bars overlap or don't overlap. Consider that on this graph, to do that, there would be 24 bars, each with error bars. That's 276 pairwise comparisons that this graph is implying we should be making. Were all those comparisons actually made in the analysis that accompanies this graph? Should the reader be considering them all now, given that they are all shown? At The average person can make about 3 pairwise comparisons in a second. That means that this graph would take me a minute and a half to interpret. That's an awfully long time, right? Can the audience even appreciate and integrate all those comparisons that we're asking them to make here, right? Consider that presenting group means and standard deviations in a table is actually really efficient. So, did these things need to actually be conveyed in graphical form instead? Do the error bars contribute to our message or do they muddy it here? I'd actually argue the likelihood is probably the latter here. So we could have visually de-emphasized them and emphasized the comparisons we really cared about, but I think we probably could have omitted the error bars here and not lost much of anything. So to recap here, your graph should have a message. Readers should be able to quickly find it and evaluate it critically without not having access to the data that they need to be able to do that, of course. And we should be selective about what we graph to help our reader do that evaluating as efficiently as possible. Okay, that takes us to principle number 3, which is all about making our graphs work for every potential reader. For those of you who aren't familiar with it, UD or universal design is a design philosophy that says you should design things such that they are usable to as many people as possible, regardless of things like age, race, language, nationality, ability, and so on. The idea is to maximize your audience, which as scientists is exactly what we should be wanting. In particular, UD would contend that as visual media, graphs need to be sensitive to those with visual impairments in particular, as well as those with less sophisticated viewing or printing technologies. For example, we should consider those with visual impairments when we are designing our graphs, such as those who would struggle to read small text or discern or separate small elements from each other. I'd consider my eyesight to be decent, though I do wear glasses, but I can't read the point labels on this graph very easily. As such, we should make all the key elements in our graphs as large as we possibly can make them. I would argue just shy of making them look ridiculous. In other words, text and key elements should be quite big, much bigger than we usually make them. Here's the adage I want you to keep in mind. If your eyesight is average in your opinion, then things should probably look too big to you to be big enough for someone with a visual impairment. especially considering visual impairment increases with age, and we are increasingly aging species. So this will only become a bigger problem as we move forward. Second, universal design graph designers would encourage us to embrace white space in our graphs. Many of us treat white space on a graph as wasted space, but our eyes actually need some amount of white space to be able to easily separate nearby elements from each other. Without it, parsing elements becomes quite taxing. So, for me, at least, focusing on any one x-axis label in this graph is hard work for me. Whenever we can, we should be separating elements from each other with a buffer of white space. In particular, here are three places to increase the amount of white space that you use in graphs most of the time. You should look to increase the space between axis titles and their labels, between labels on an axis. So if there was some way to get fewer labels on this x-axis, that would have been nice. You could have also cut some of the labels on the y-axis here to space them out a little bit more. And you should increase the white space between elements inside of the graph that you don't want compared to each other, because we innately want to compare things that are next to each other and not compare things that are further apart. So by spacing them apart, it makes it actually easier for us to parse what comparisons we should be making. In each of these instances I've just described, white space is actually doing work for us. It's helping our eyes read what we need to and giving us an ability to take rests in between those things. And it also tells us what we can afford to ignore in a graph. Third, and fair warning, this one's kind of a doozy. Data viz experts would caution us against using color. Color! What monsters, right? Seriously, though, color should never be your first choice when you are designing your graph. And I say this knowing that it is one of the things we reach for first in many cases. So if this is a culture shock for you, believe me, I get it, right? If you really need convincing, though, I have 10 bullets explaining in excruciating detail why data viz experts say this. I'm not going to read them here, but I will encourage you to pause the video to do so if you are curious. Instead, I'm going to highlight a few of the issues with color for accessibility on the next few slides. Just know that even this list on this slide is not exhaustive. That is how problematic color can be in graph design. So, I'm going to try to convince you, but let it be known that there are a lot of issues with color beyond the ones that I'm about to highlight in the next couple of slides. First, we need to recognize that nearly 10% of humans are color vision impaired in some way, even if that doesn't quite rise to the level of color blindness. However, on the flip side, 1% of humans about can't distinguish colors at all. They have grayscale vision or less. Red-green color blindness specifically affects nearly 5% of human males. So those individuals with that kind of color blindness would not be able to distinguish many of the lines on this graph from each other, for example. Beyond this, color printing and even rich color viewing on a viewing screen is still a privilege in many parts of the world. So we must consider that our work may not always be consumed in color, even if we use color in our graphs. So we have to ask ourselves then, can our graphs still be consumed usefully in those cases? A popular design adage in this space is get it right in black and white first. That is, let us try to design our graphs by first considering all of our available non-color options. Is color really necessary or efficient to convey the message we're trying to convey? If it is, fine. But let's, in that case, always opt for a colorblind friendly palette. If you've not heard of these before, what they do is they vary both hue, which is the colors like red, green, purple, pink, and luminance, which is how bright something is or dark something is, so that things are different in both luminance and hue. The Viridis palette is the most well known of these. There are other colorblind friendly palettes out there. Viridis is not the only one, though it is the most well known. Even in the instances where you're going to use a colorblind friendly palette, I want you to consider that if what's really conveying meaning in those cases universally is luminance or saturation, and thus those things must be working to convey information, do you really need to add color hue on top of that? What is color hue adding in that case? Actually, not very much. Okay, let's talk contrast next. This is the ability to distinguish two nearby elements from each other based on their color differences. One common issue is that some colors will fail to contrast with those that are behind them. So, bright colors, especially yellows, pinks, cyans, and oranges, often have low contrast against light colored backgrounds, like those that we tend to use in graphs. More generally, related colors often will lack contrast with each other. For example, it's often hard to read blue or red text on a purple background. This can be an especially big issue if we need to use many different colors in our graph to separate many different groups from each other. Here's a graph, for example, that needed to use 5 different colors. And these here all I would say are pretty distinct. But if we instead needed 7 colors or 14 colors, the odds that at least 2 colors would be too similar to be readily distinguished from each other would go way up. Plus, I would say here too, for bonus points, that yellow in this graph is probably too light if our background was white instead of gray. So, contrast is a very typical problem when we're trying to use color, which is another good reason to not always reach for color first. We should also consider that colors are interpreted not just visually, but cognitively. We associate ideas with colors in ways that can be deeply ingrained and surprisingly non universal. As one really funny example, I want you to consider this graph I just put up on the slide. It shows property damage yearly caused from different natural disasters. I want you to consider here why they made wildfires green instead of orange. Why did they make flooding orange instead of blue? Why is drought blue instead of yellow? Consider how unintuitive these color choices are in this graph and the cognitive load it may then take to undo them to be able to read the graph properly. Another really interesting example is red. Red is strongly associated with bad in Western cultures, especially here in the United States. If you make the positive end of a color spectrum red, readers will frequently interpret your graph backwards. However, even that isn't universal because many Asian cultures, meanwhile, will associate red with good fortune. So they may actually interpret your scale the opposite way around from those in the West would interpret it. So, cultural associations are another tricky thing that you would have to navigate if you chose to use color in your graphs. Another big challenge with color has to do with how our eyes perceive it. We don't perceive color absolutely when there are multiple colors around it. Instead, we actually perceive it relatively. We compare each color to those around it to figure out what color each color is. So, consider this image. Do the inner squares in this image look like they are the same color, or do they look like they are different colors? If you think they look like different colors, they aren't. They are the same color. However, most of us will view them differently because the color that we are comparing them to is different. We're always comparing them to the color right next to them, and that affects our perception of that color. So this happens on multi-color graphs all the time, especially those like heat maps that are forcing us to compare colors that are in close proximity to each other. This is what is called the simultaneous contrast illusion, by the way. Colors also feel very discrete to us humans. We like to see red and yellow and blue as distinctly different colors that are very far apart from each other, which means we always want things that are colored differently to be significantly different from one another. Here on the slide, we have 2 maps that are showing the exact same data, but they are doing so using different color palettes. A color palette that involves a lot of color hue transitions and one that doesn't result in nearly as many color hue transitions. What we see here is that we have data that are varying continuously, but in the first graph, we are going to notice a lot of pockets of difference, especially wherever the yellows and the blues and the greens start to appear, because those colors feel very different from the pinks and reds that are present on the graph elsewhere. However, we can see that a lot of times those differences that our eyes are pulling out in the first graph really are not that dramatic. We can see that in the bottommost graph, where a lot of those things that feel like there must be a lot of transition actually aren't very much transition there. The transition between some pairs of color is very quick in some palettes, but gradual between colors in others, which also doesn't help here. Plus, I will say bright colors, colors that are high in luminance, like yellows and oranges, tend to jump out most to our eyes, even though those are tend to be intermediate colors in most multicolor palettes. For example, in this rainbow palette here, yellow is actually in the middle somewhere, even though it's something we're going to want to innately view as high. All of this is to say that it's much harder to do color right than it is to do it wrong. Even if we like the look of a graph with color, that's not enough of a reason by itself to use it, unfortunately. Now, graphs are also interpretive media. We must expend mental energy to be able to interpret a graph, whose elements may represent information abstractly rather than literally. UD encourages us to consider cognitive impairment as well when we are designing a graph for this reason. In other words, can we reduce the cognitive load that is needed to interpret our graphs? If we can without sacrificing something, then we should try to do that. One thing we should certainly try to do then is remove any element that doesn't really need to be there because it's not conveying information in some valuable way. So this kind of harkens back to a point I made earlier in the video. For example, a lot of graphing software will include a gray background and bidirectional grid lines by default. You can see both of those elements in this graph on the slide. The background here, though, is conveying no information. But because it isn't white, which means it isn't void space to our mind, we must mentally process it, realize it doesn't do anything, and then ignore it. So that's not terribly helpful, right? Interestingly, here it is also reducing contrast between it and the colors in the graph itself, which are conveying information. So white would be better for both of these reasons. Second, grid lines, of course, are designed to help readers more easily determine exact values. However, remember that graphs are primarily about vibes. Exact values are not well conveyed by graphs anyway. So grid lines are usually unnecessary and they clutter the plotting area up. At least I would recommend thinking about thinning them or desaturating them by making them gray or eliminating them in one direction if you really only need to be making comparisons in the other direction. Another common issue, though it's not shown here, is thick top and right-hand side border lines around the plotting area. While X and Y axis lines convey information, their counterparts on the other edges usually don't, and they can be removed without any loss. These are sort of the border lines that frame the other side of the graph. Oftentimes, those aren't necessary. Lastly, even seemingly required elements can sometimes be cut in an effort to reduce cognitive load. Here, for example, I would argue that the data on the x-axis of this graph is so clearly years that we probably don't need to call attention to the fact that they are years. We can probably just eliminate the x-axis title in this particular case. So, a good rule of thumb in that frame of reference is dry, DRY, don't repeat yourself. If it's redundant, cut it. If it's very clearly years on the x-axis, then adding year is essentially repeating ourselves. Another important reminder that we all need from time to time is that our audience as scientists is global. Not all of our readers are going to be familiar with our specific customs, our local geography, our native language and idioms, our conventions, our study system or species or methodologies. Thus, we should be mindful when using anything not readily translatable. For example, in this graph uses abbreviations for bird species. But does it need to? Could it have just used the full names of the species in question, right? Then I don't need to remember what this crazy acronym means. It's also acronyms of the common names of these species, which are going to be less meaningful for an international audience and probably should be replaced by the scientific names instead, right? A good graph can stand alone, meaning that the reader doesn't need you or the paper available to make basic sense of it. Any way that we can be as plain languagey as possible in our graph is going to help us be able to do that and appeal to a wider audience. One last idea to consider for this principle is asking if we can consolidate the info that a reader needs in some way. If we spread needed info out between the plotting area, the axes, the legends, the caption, and the text of our paper, the reader is going to need to jump their eyes all over the place to integrate that information, and that makes the task more cognitively difficult. One way to reduce that burden then is by finding ways to eliminate something like a legend, such as labeling groups inside the plotting area instead, right? This is functionally the same as a legend, but it didn't require me to have a legend that then someone's going to have to integrate across. Another way that we can do this is by moving information like sample sizes or statistics that are often found in the surrounding text or in the caption inside the plotting area. In this particular instance, there's an awful lot of void space down here in the graph, probably more than we need. This is an opportune place to think about putting that kind of information so that it's closer to where I'm seeing the data that I might be evaluating with that information. You should also help your reader find the information that they are looking for more easily if you can. So, if you can sort the groups in a figure alphabetically or from highest mean to lowest mean, for example, that's another way that you can decrease cognitive load. Okay, let's move on to principle number 4, which is a reminder that when it comes to channels, you have options, far more of them than you might think. I should define what I mean by a channel. A visual channel is a fancy way of saying a way you can visually encode data in a graph. Many of these are actually things you already know. For example, position on the X or Y axis is used in many graphs to convey information. Length is used to convey information in a bar graph, and color, hue, and saturation are used in graphs all the time, as we've already discussed, even though, well, sometimes they probably shouldn't be. You're also probably already familiar with shape, color, and area being used as visual channels. However, there are many other channels out there. Consider that direction, rotation, or angle could be a channel. One group could be triangles that are pointed straight up. Another could be triangles pointed not straight up, like to the side, for example. That might differentiate groups. Line end type could be used to distinguish groups on a line graph. You could use square, circle, arrow, or blunt ends as for examples there. Groups could also have bars that have different levels of corner rounding or border lines. There are something like 20 common visual channels that we could be using in our graphs, but we often restrict ourselves to the same 5 or 6 every single time. And this principle reminds us that that is not very creative and maybe suboptimal in many instances. So, this principle asks us to prefer some channels over others as well, because they might vary in how accurately the human eye can actually interpret them. As one example, one-dimensional aesthetics, such as length, are always going to be easier to compare than two-dimensional aesthetics like area. For example, if you're trying to compare the wedges in a pie chart, you are going to do that less accurately than you would be comparing the lengths of bars in a bar chart. If you can get down to 0D aesthetics, such as x-axis position, for example, that's going to be even more accurate still. If you instead make me compare three-dimensional dimensions like a volume, that's going to be even harder than comparing area. So this is another reason why data viz experts prefer bar charts to pie charts. The latter is going to make comparisons harder than necessary. Now, of course, three-dimensional graphs, which I should mention here, such as this three-dimensional scatter plot, are almost universally discouraged by the same logic. They are really hard to read. What is actually going on with the gray points in this graph? I want you to pause here and consider. Is sepal length increasing from left to right, or is petal length increasing from left to right, or is both increasing, or is it actually sepal width that is increasing from left to right, right? From our viewpoint into the graph, it's actually impossible to tell. So, unless these graphs can be interactive so that readers can rotate them freely and get their own viewpoint, 3D graphs should always be avoided. Three-dimensional position is too hard of a channel to interpret accurately. When choosing channels, we also must resist a common temptation, which is to double map them. That is when we use two channels to convey the exact same information. This violates that dry or don't repeat yourself principle that I was talking about earlier. For example, we have a bar chart here where we have fill color hue reflecting different cuts of gems. However, I want you to notice that the x-axis position on this graph is also cut quality of gems, right? So we have color hue and we have x-axis position conveying the same information. And in this particular case, the latter is sufficient to do the job. If all these bars were gray, you would still be able to read this graph with no loss in interpretability. Yes, the graph would be less pretty. I will concede that point. However, consider that being pretty is not the primary purpose of a graph. The primary purpose of a graph is to convey information. Here, color isn't actually helping us do that. We've wasted it. We might have been able to use it somehow to encode new other important information, but we didn't, and now we can't because we used it in this redundant way instead. More importantly, though, people don't generally assume that channels are double mapped. When I see a graph like this, for example, it actually takes me several seconds before I realize and conclude, oh, right, okay, color isn't actually telling me anything new here. It's just meant to be pretty. That's time and energy I spent trying to figure out how I'm supposed to read your graph instead of reading your graph, which is not what we want, right? So I will challenge you to pay attention. I bet that you will see double mapping of channels all the time in graphs, especially with color. And it's another good reason to avoid using color as a visual channel, at least at first, because it is so tempting to double map it. One last point to make about channels is that we sometimes forget we can use several graphs to tell a single story rather than smashing a big story all up into one graph. So you can divide one graph into subpanels, each showing a subset of the data that would otherwise have been in a single graph. When you do this, you are effectively using panel or panel position as a visual channel to communicate information. This is called faceting in ggplot and R, and it can be a really effective way to reduce cognitive load in your graphs. All right, next up, principle number 5. I like to think of this one as the obligatory let's all use common sense principle, even though we all know that common sense isn't always that common, right? There are some things that I would say great graph designers rarely, if ever, do. I think in many cases, if we just stopped to think about these things a little bit more or had them pointed out to us, we probably realize that they aren't the best practices we could be using. But even the best among us sometimes need a reminder about these things. So that's what this section of the video is going to be about. First up, hopefully this goes without saying, but if we're going to be using colors in our graph, maybe we shouldn't reach for neon colors. Those tend to be quite garish, right? You should be trying to choose colors that actually play nicely together visually. Beyond the considerations we've already discussed for color, though, if you're going to use them, I would recommend that you use desaturated tones. Those are the ones that have a bit of gray mixed in. Most people in most studies tend to report that they think those look more professional. So instead of reaching for neon colors, you should actually be reaching for the opposite of that, things that are very muted and desaturated. Also, there are tools out there that will help you select a suite of colors that look good together. So you should never be haphazardly picking colors because you have a very good chance of picking ones that may look distinct at a pairwise level, but they look awful together once you actually get them on a graph. Second, remember that data often have units and that those units should be obvious in our graphs. If possible, we should be stating them right in our axis titles and not burying them in the captions or in the text. Also, I think you should be considering whether your units are as simple as they possibly could be in a graph. This graph, for example, uses thousands of meters on the x-axis, which requires them to have up to 5 characters to represent every label. They could have just used single kilometers here. And that's kind of an unforced error, in my opinion, because it would have simplified the graph. And we're all just about as good at interpreting kilometers as we are thousands of meters. Hopefully, this one also goes without saying, but please proofread your graphs for the love of all that is holy. Many papers that I've been reviewing lately seemed to have forgotten this rule. The figures were way more air filled than the surrounding text, and that is a shame when people might be starting with your figures. This is especially important because graphing software will often do all kinds of goofy stuff by default that needs fixing, and you need to go in and try to fix it or look for it, right? Unnecessary capitalizations is one that I see all of the time. So I would definitely encourage you to be, in particular, really consistent and vigilant with your capitalization in your graphs. Here, I actually can recommend using sentence case, which is capitalizing the first letter and any proper nouns or abbreviations and leaving everything else lowercase. We tend to get a little trigger happy with the shift key and we capitalize letters we don't need to. So that's something that I would recommend being vigilant about. This next one is a bit of a pet peeve of mine, I will admit. Remember that axes are continuums that run from some number up to some number. They are essentially number lines. As such, it's helpful to know at a glance what the endpoints of the number lines are. There should be labels at both endpoints of your axes. In this particular graph, there's a large chunk of space here to the left of the leftmost label on the x-axis. Same goes on the right-hand side here, right? You need to make sure that your graphing software is labeling those endpoints. It's very common for labels to end up being truncated like this when the data don't quite make it all the way to the next whole number. So a label doesn't get put there by default. To me, this reads like accidental incompleteness, and it also makes it harder for me to make like immediate sense of what values these points in the end regions correspond with, right? It's an easy fix. We just need to expand the x-axis limits a little bit until we get to the next whole numbers on either side, or we need to change where the axis breaks are. Maybe we needed to do 1.5, 2.5, 3.5, 4.5, 5.5 here instead if we didn't want to extend the limits. So, since it's such an easy fix, there's really no reason to just accept it being like this. More broadly, it's good to use the same design choices across all the graphs in the same paper or presentation. That way, readers could only need to learn one set of rules to understand all of the graphs in your product for the most part. Plus, we've all seen papers that have graphs that clearly were produced by several different people at different times using different styles and different softwares. I can't be the only one out there that thinks that looks really sloppy. So, here as an example is two graphs I pulled from the exact same paper recently. It's hard to tell that these two graphs are from the same paper, aren't they? They actually are showing quite related data. It means that I can't take much from my experience with one of these graphs into understanding the next graph. Each graph is essentially like starting over, which isn't good and it wasn't necessary in this particular case. Another pet peeve of mine is plot titles. I know that we were all taught in high school that we should use a title when we are making a graph, but in truth, scientists very rarely use them, at least in papers. Presentations are and posters are a different matter, but in papers, we very rarely use them. Why? Titles tend to do what a figure caption already does, but it does that worse than a figure caption would. So when we have a caption, which we almost always do in a paper, we don't need the title too, right? So I have a graph here up on the screen that shows this in action. It is not uncommon for a title to not just repeat the figure caption, but even sometimes to just repeat the y-axis title, because that is what it is doing in this particular case, right? DRY, don't repeat yourself. Figure titles are often a very easy way to do that, sometimes by accident. Another thing to avoid for sure is what data viz folks would call chart junk. This is anything that you place in a graph that is there purely for appearance and not to convey information, and which might then distract from the interpretation of the graph. This includes background images, clip arts, icons, animations, word art, and pseudo three-dimensional effects, which are where you add an artificial depth like you are doing here on this pie chart. Consider that here, this third dimension, this height of these pies, is completely meaningless. It conveys no information. So the reader has to first determine that, and then they have to ignore it. Worse, though, in this particular case, to add that third dimension, we had to stop having the pie being looked at from above and instead have it looked at from the side, which means now some groups are in the foreground and other groups are in the background, which means they are now more difficult to compare because we have a perspective shift. Things closer to us look bigger than things farther away, right? So in this graph, is the orange pie slice bigger or is the yellow pie slice bigger? It is actually really difficult to tell that thanks to this perspective. So by adding that pseudo third dimension here, not only do I not think we made our graph prettier, but we actually made it less interpretable as a result, which is a real shame. However, the biggest no-no when it comes to graphs from a professionalism standpoint, in my opinion, is of course using our graphs to distort our data or mislead our reader. Data viz experts will tell you there are 1,000 ways to mislead using graphs. I'm not going to go into depth here on these because many other guides have done this subject much better than I can. But I do want to give you just 3 examples of how just messing with the y-axis scale of a graph can allow you to hoodwink or confuse your readers. First, I want you to consider this graph, which shows gun murder rates over time in the state of Florida here in the United States. I want you to think for a second. Does this graph support the argument that Florida's Stand Your Ground law, which was passed in 2005, caused gun murder rates to drop? Well, I will say abstractly looking at the graph, that is certainly what it looks like until you realize that bizarrely the y-axis here is backwards. As we go downward, we're getting more murders, not less, which is probably contrary to most people's expectations, right? So you can imagine how someone who is reading this graph quickly would misinterpret this graph. And I wonder in some ways if that was almost the point here. Okay, now I want you to check out this graph. It shows COVID case rates in the United States over time during the year of 2020. It looks to show a relatively steady rise in cases over time. But I want you to look closer at this graph. What is going on with the y-axis and what would be the impact of that? Did you catch it? The first step in the y-axis is from 0 to 5. So that's a 5,000 point difference. But all the remaining steps in this graph are 15,000 step differences. So right when the rise would have started to look much steeper, we switched our y-axis scale to one that will make the difference look less steep, right? That's quite interesting, right? So this graph was made to look less impressive than it otherwise would have. One last example, it's kind of a dumb one, but it works. This graph shows the average home prices for 2 different years. And the plot title here is saying that we've got a massive increase over last year. And certainly the bars make it seem like there was one. But again, I want you to check the y-axis here. The difference is actually only $2,000 or about 2.5%, right? I'm not saying 2,000 isn't a large amount of money. It is, but it's 2.5% difference, right? I want you to consider what this graph would have looked like if zero were on the y-axis instead, right? These bars would be virtually indistinguishable in length, and that would be sending a very different message, right? So, to paint with a very broad brush here, the rule of thumb is that if your test or analysis has a null hypothesis value, which is often but not always zero, that should probably be on your graph somewhere. Your axes should also be going in logical directions, and the steps between labels on every axis should always stay consistent. To do anything else is probably creating a graph that's going to mislead your audience. Okay, that brings us to the last principle, which is not about graphs themselves, but their long underappreciated captions. If people aren't paying enough attention to their figures, they're really not paying enough attention to their captions. And that's a shame because if graphs are superheroes, captions are their sidekicks. They accompany graphs and ensure that they can stand alone by explaining everything that the reader needs to be able to digest the graph successfully, just as well as we could digest it as graph designers. And when I say everything, I do pretty much mean everything. Captions might have to contain a lot of different things, although not every caption needs everything that I'm about to list here. In general, here is what a good caption will contain. A good caption will state the graph's purpose. What is this graph doing? What is it for? Which argument in the text is it relating to? You will make some connection there. Often, it will also provide context for the data that are shown in the graph. Where and when were the data gathered? How, generally speaking, were they gathered? Sometimes we can't actually meaningfully evaluate the data without being told that information. And if you tell us that stuff in the methods, now we need your method section to be able to make even basic sense of your graph, which is not meaning that that graph is standing alone, right? A figure caption may also contain what I would call a call to attention. This is a way of pointing out where in the graph the message is that the reader should be evaluating or pulling and what that message is in a nutshell. For example, if there's a trend, what is that trend? Where is that trend in the graph? How is it marked if that is not already obvious, right? Anything else readers need to be able to critically evaluate the message of our graph should also be in the caption. So this should include things like details on any stats performed and sample sizes. And of course, I hope this goes without saying, a caption should be clarifying anything about the graph and its channels that need clarifying. What are those colors? What are those symbols? What are those abbreviations? What do the subpanels represent? What are these treatment codes? If anything is not self-evident, the caption is going to make it evident. Just as importantly, there are things a good caption does not usually contain. For one, it should not include interpretation. And that might sound confusing because what is a call to attention if not interpretation? Well, a call to attention is really a statement of fact. There is a trend here. It is significant. Its slope is X, and so on. All of what I just said would fall safely within the bounds of what your analyses can objectively conclude. Interpretation is, meanwhile, what we do in discussion sections. It's where we speculate on why a trend exists, or what it means practically, or why other studies haven't found this trend, or what have you, right? All of that doesn't belong in the results, and thus it does not belong in a figure caption. Another thing a caption shouldn't include is us repeating ourselves, either by clarifying things that are self evident already in the graph or by repeating something that the graph already says. For example, do not repeat the X or Y axis titles in your captions. Also, do not start a caption by saying a bar graph of. If a graph is already obviously a bar graph, you are insulting your reader by telling them it is a bar graph in your caption. Detailed methods also do not belong in a figure caption. The reader just needs the gist for context. They can always consult the methods if they need to know a lot more. They just need enough to understand where the data are coming from. On the flip side, you cannot just say, though, see methods and be done either, right? A figure can't stand alone if you need the methods to make any sense of it. The reader needs to be able to get that gist, even if that gist is brief. And of course, don't introduce entirely new or entirely irrelevant things in a caption. For example, don't define a term for the first and only time in a caption, especially if that term has nothing to do with what's being shown in that graph. I hope that goes without saying. If this all sounds like a lot to include and to not include in a figure caption, I would say, well, I have news for you. It is. In my experience, it is rare for a 1 to 3 sentence figure caption to be sufficient, even though I see them all the time. That said, I do think it's quite possible to write a brief but effective caption, as many of these bullets that I've shown on these previous two slides can be relatively easily handled in just 2 sentences each or less. And good graph design, by the way, makes a lot of clarifications in your figure caption unnecessary, which also shortens them. Now, it's tricky to do a deep dive into captions in a video because they're bulky written entities, which is not exactly captivating video content. But in light of the two lists I just presented, I think it'd be useful to critic one sample caption and consider what it does well and not as well. So here is a figure and a caption I pulled from a recent paper that I read, and I pulled its figure caption as well. And this is also one of the figures that I consider in the case studies section on my online guide if you want to know more. What I would encourage at this point is pausing the video, looking at this figure, reading this caption, and asking yourself, what does this caption do well? What's it missing? And in what ways could I improve it based on the lists I provided on the previous two slides? Now, in the online guide, I remade this graph and its caption from scratch. You can go find my new caption in the guide, but I've also, for your convenience, pasted it here on the right-hand side of the slide, and the original figure caption is on the left-hand slide here for reference. I will admit that I remade the graph, and so some of my captions contents relate to that new version, and there are elements in there that are new in my version that wouldn't have been applicable in the original anyway, so keep that in mind. However, I would say most of the elements apply to both versions. I also want to apologize here for the small font. It was hard cramming all of these on here, so hopefully this is readable for most folks. I would encourage you at this point to pause the video again and compare these two versions of this caption. What did I add to mine? Why do you think I added it? Which version do you prefer? And which would help you better evaluate and read the figure? That's the really key one. I would personally argue that I've added a call to attention, which wasn't there before. I've added more context about the where and the when for how the data were gathered. I've added information about the statistics here that weren't included before. And I've provided greater clarity about where the abbreviations are coming from that are used in the graph. Yes, my version is longer by about 25 to 50%, I think, but it means the reader now has access to much more context than before. They now don't need the paper at all to make full sense of this graph, which I'll note was quite complex to start with. So the reader did need some help in understanding this graph. If you liked that exercise of comparing two versions of graph related elements to each other, I'd like to close by reminding you about the digital version of this guide. You can find it at the URL here at the bottom of the slide, z.umn.edu/great_graphs. There you can find the case studies page wherein I take real figures from papers like the ones here and critique them, listing what I like about them and what I like less about them. I then remake each graph using simulated data to hopefully better align with the principles that I've been summarizing in this video. In fact, you can see my new version of this graph on the right-hand side of this slide. I go into greater detail about all the choices I've made in the guide, And on top of that, I provide annotated code to make these graphs in ggplot2 if you would like to know how to do that. So I encourage you to check it out. In the meantime, I want to remind you that my name is Dr. Alex Bajcz. My email address is here on screen, bajcz003 at umn.edu. If you'd like to reach out and discuss graphs and graph design, feel free. I'd be happy to have those conversations. And as a shameless plug, if you're looking for guidance on how to turn all this theory about graph design into action now, I also have a guide to the R graphics package ggplot2, which you can find at the URL at the bottom of this slide, z.umn.edu/ggplot. So we could talk about that too if you wanted. To close, I want to thank MASERC and MASERC's funders for allowing me to produce this video and guide, including the state of Minnesota, the Environment and Natural Resources Trust Fund, and the Legislative Citizen Commission on Minnesota Resources. Thank you again for watching. I hope you have a fantastic day and good luck leveling up your graphs. I can't wait to see them.